This is a video about something called vibrational modes. Vibrational modes. What a fancy term. Another fancy term we can use at parties to impress our friends. Yes, that's what physics is. Okay, fuel for impressing our friends. No, it's more than that. This video is about vibrational modes, but to understand what that means, first let's ask the question, what is it that has these different vibrational modes? Well, the answer is standing waves. Okay? And what is it that produces a standing wave? In order for a wave to exist, we need a medium. And in this whole example, this whole video, our medium, what will be vibrating to produce a standing wave, will be a piece of rope tied at both ends. So let's get rid of this and this just for the time being. And let's look at our piece of rope. Here's my piece of rope, and I've tied it down at both ends. It's tied down. Now, this is a very, very important fact about our piece of rope. Let's see why. Let's say I want to, okay, first, this rope, this is just an example, and this is not something to write down in our page. Don't write this down. I'll tell you what you want to write down in the notes page that you have in front of you. So, pretend for a second that this rope has a length of 1 meter. Will it be possible for me to produce a standing wave on the rope whose wavelength is 1.1 meters? Well, let's draw a picture to see if that would be possible. One full cycle of this hypothetical wave would be stretching a distance of 1.1 meter, like that. So can I possibly cause my wave, the black line, my string, the black line, is it possible to cause that string to vibrate to produce this 1.1 meter wave? Clearly the answer is no. Why is it? Why is the answer no? Well, it's because our string is tied down at the end. See that? So in order to produce a standing wave, there's a criterion, a condition that must be met or satisfied by that wave. Only waves that have a node at the end of the string can be produced. Why must the end of the string be a node for our wave? Well, because we're tying that end down. So this fact is called a boundary condition. The fact that it's tied down, the fact that we have a node at the end, is a boundary condition, because that's the boundary of our string. That's the edge, the boundary. Okay, so clearly a 1.1 meter wave doesn't fit, because when we get to the end of 1 meter, oh, here we go, we're traveling along, we look, and we get to the end of a meter, and we're not at a node. This here is not a node, and so it's impossible to create that kind of wave with that length on a 1 meter string, because on a 1 meter string, we're tied down at the end, and there's a node there. There has to be. So, what we've just shown is that only certain waves will fit onto this string whose length is 1 meter. So if you take a string, and this is what I want you to draw, whose length is L, and then leave a little space. The length of the string is L. We can only produce certain types of vibration. That's what the modes mean. A mode is a certain type of vibration. Right? And we're going to figure out what exactly those modes look like and do a little math. So let's say, now don't draw this, let's say we start with our piece of string here, our rope, and I, flick it in the middle with my finger, okay? I just flick it right in the middle, and that middle section starts vibrating up and down. So it starts like this, and then it goes to that, and then, let's get rid of this. After a little more time has passed, it goes back down to its middle position, and then it vibrates down to here. Oh, that's not very good. Vibrates down to here, and lastly, it's down like this. Because I flicked it in the middle, I have an antinode there. That's where it's moving up and down with the greatest displacement. And at the two edges, we have nodes. Right? So what should you draw? Just draw the black line. Don't worry about red, green, blue, or purple. Just draw the black line. And you know what? I'm not going to worry about those colors either. That was just to show you what the wave does. Right? Because I don't have a fancy animation. All I'm doing is drawing it, and I can't draw a passage of moments. Okay, so here's what we call the first mode. Oh, wait, here's what I want you to write down. This is called the first mode of vibration. That's what we've just drawn. And I want you to get exactly what I have here so far, the first mode. Now, why is it the first? Well, the answer is we can't have any fewer number of nodes. Right? If we start with the smallest number of nodes possible, this is what we get. Because you can't have less than 2 nodes. You have to have a node at this edge and a node at this boundary, this end. So that's the first mode. Now let's think about a wave. Here's what a general wave looks like. And if we only have one crest, like this, right, how many cycles have we fit onto the string? Well, this is what is on the string, but a complete cycle is this in blue, and so clearly my red crest here is just half of one complete cycle. Half of a complete cycle. So if this is half of a cycle, it stretches a distance of half a wavelength. Don't draw this. Don't draw what's in red. It stretches a cycle of half a wavelength. But what I've just drawn in red is the length, L. It's this length. So the length L equals half a wavelength. And that's what I want you to draw, is what's in black there. So draw that. This is all going in the first box on your paper. Okay, time for the second box. That's what I'm going to put down here in this space. If we start with this equation, L equals lambda over 2, we can multiply both sides by 2 in order to isolate lambda. And what do we get? We get 2L equals the wavelength. So if we take this, we can plug it in to the wave speed equation. Right? Actually, I'm going to isolate the frequency first. So I'm going to divide both sides by a lambda. The lambdas cancel on the right, so I can erase them because lambda over lambda is the same as 1 over 1. And when I multiply by 1, I don't show times 1. And so now what we have is frequency is wave speed divided by lambda. So what I want you to write, you can write this step if you'd like. You can show the work. But I want you to write F equals V over, not lambda. I'm not going to write lambda. I'm going to replace it with 2L. So I've substituted in for lambda using 2L. Because lambda and 2L are replaceable in this first example of a standing wave. Right? They are replaceable. And let me get these out of the way. Move these over. So there are some important equations here. This is the first important equation. Here's the second important equation. This is the first mode. Time for the second mode. Here's my string. And this time I flick it, maybe with 2 fingers, in such a way that there's a third node. So I've increased the number of nodes by 1. This is the next way we could cause the string to vibrate. Right? If we're increasing by 1 node every time. And we call this the second. It's the next, the one after the first. So this is the second mode of vibration. And here's our wave, right? Between every 2 nodes, we have a crest followed by a trough. So what does the second mode look like? What's the string look like at some snapshot? Well, at one snapshot, it looks like this, a crest followed by a trough. So draw that. Draw that. Now, we have the same string, so it has the same length as before. And this time we look and we see we have fit one complete wave cycle onto this string. So one wave cycle stretches a distance of the wavelength. So now we can say that lambda is equal to the length. And I'm just going to draw this, don't you draw it. But after a little time passes, our wave will look like what I've shown in red. And then after a little more time, it'll vibrate down back to the center position. Then after a little more time, it'll vibrate like this. And finally, it'll go to the bottom before moving back up to the top and just repeating. It just keeps going up and down and up and down. Right? It just keeps going back and forth. Okay, that's just to show you what's actually happening as time passes. My black line is just a snapshot moment in time. So, what are we going to draw? What are we going to write in the bottom box? Well, let me move this down. Oh, whoops, hang on. That's too far. So in the bottom box, let's start with L equals lambda. We've already isolated lambda. So we can come back. If we look in the previous box, that's the wave speed equation after isolating the frequency. So we can say that the frequency is the wave speed over L. Since in this second example, the wavelength is replaceable equal to L. Right? The thing that's in the circle is equal and replaceable with the thing that's in the square, thanks to this equal sign, which is now in a triangle. So many shapes. Oh my gosh. Oh, that's not supposed to be there. Okay. So let's take this away. We don't care. We don't want our circles. Box this equation and box this equation. So these are important equations. Yeah, for the second mode. Now here's the third mode, the third and final example. I mean, this is really easy. You could do this on your own by now. Instead of having 2 nodes, instead of having 3 nodes, we're adding one more, right? We're going to add another so that there are 4 total nodes. So 2 in the center instead of 1. Right? In the last example, oh, here it is. In the last example, we had 2 nodes right there, 3 nodes. Wow, let me practice my counting. 1, 2, 3. And in the one before that, we had 2 nodes. Right? So now we have a total of 4 nodes, and between every 2, there's a crest followed by a trough, like that. And this is the same string. It still stretches the same length L. Right? And how many wave cycles have we fit onto the string this time? Well, there's this one. That's clearly one complete cycle. But look, there's another half cycle after that. So how many cycles have we fit? Well, 1.5, which we could say are 3 halves. So 3 halves, well, let's say it this way. 1.5 cycles, which is what I've drawn in red, 1.5 cycles, span a length of 3 lambda over 2. So L is equal, in this case, 3 lambda over 2. And we call this is called the third mode of vibration. And let's label our nodes. Here they are. And this time, we have 3 antinodes. Antinodes we mark with an X. Oh my gosh, let's go back. Did we mark our nodes and antinodes? Node, we didn't. Oh, we didn't do it. Node, that's bad. Let's come back to the second example, the second mode. That had 3 nodes and 2 antinodes. Okay. So look, the second node has 2 antinodes. Back to here, this is our third. This, of course, is the third mode of vibration, the third vibrational mode. And if we go to the bottom box, right, we're going to the box below it, we can fill in that information. Let's extend, whoops. Oh, that's where I was hiding those squigglies. So now we can start with this equation, L equals 3 lambda over 2. I'm going to isolate lambda again, and the way I do it, you multiply both sides by 2/3, because 2 over 2 is just 1. and 3 over 3 is 1. So what do I get here? I have 2L over 3 is equal to lambda. So the wave speed equation looks like this after isolating frequency. And I'm going to replace I'm going to replace lambda with, you guessed it, 2L over 3. 2L over 3. And this is a denominator this is a fraction in the denominator, and the fraction in the denominator comes back up to the numerator. Right? So I'm going to write this, my final form is F equals 3V over 2L. And that is a box-worthy equation. So is this one. Let me move down a little. This is another box-worthy equation. We want to box that one. So the equations we've boxed, we can actually go a little bit further. This is the third mode, right? So I'm going to put a little 3 subscript here, and that's the frequency at the third mode. If I come back to this, I can come down, and I can add a 2. This is the second mode, so that's the second wavelength and the second frequency. And down at my first example, this is the first mode, so I can put a little 1 subscript. Right? Now here's the really, really cool thing. The first mode has a frequency of V over 2L. The second mode has a frequency of V over L. The third mode has a frequency of 3V over 2L. And watch this. I can add a 1 here without changing the equation. And I can multiply both the numerator and denominator by 2. And again, I haven't changed the equation. Move this down. There's a pattern here, and you can probably see it. There's an important pattern, which you probably can identify. I mean, if we were to guess the fourth frequency, we could probably do a pretty good job of guessing, right? I just take the 1, whoops, hang on. This is a 1 for the first mode, a 2 here for the second mode, a 3 for the third mode, so I just write a 4 for the fourth mode, right? F4 is going to be 4V over 2L. And what is the mth mode going to be? For some number m, right? Maybe m is 7 or 8. Well, all we have is V over 2L times m, the mode. Right? A mode of 1, we put a 1 right there where m is. If our mode is 2, we put a 2 right there where m is. Likewise for the others. Okay? So there we go. Now, last thing, let's do the same thing. Let's find the pattern for the wavelengths. The wavelength at the first mode was 2L. The wavelength at the second mode was L. At the third mode, our wavelength was, it was 2L over 3. And maybe you don't see the pattern yet, but let me take L and write it as 2L over 2. And let me write this as 2L over 1. Okay? And now we see the pattern. We're counting 1, 2, 3. Everything else is the same. Right? So the fourth lambda, the fourth wavelength, at the fourth mode, if we wanted to write it, would be 2L over 4. You just keep counting up. And the mth lambda is going to be 2L over m, where we can replace m with whatever mode we're dealing with. So m is the mode number. And there is our equations. These two equations, we can just remember these. We never have to think about these other equations that we looked at, right? We don't have to worry about, where are they? Let's go back. We don't have to worry about these because we've just derived the general form. And we will be using these two equations in red boxes, which are inside a green box, which is inside a blue box, which is inside a green box, right? And that green box is inside a purple box. We're going to use, these are so important. These are worth like 15 boxes, but I'm not going to waste the time to draw them all out. So we will use these equations to solve a couple problems.